So folks, as a reminder, we were talking about the concept of, reaching an equilibrium, how, the concentrations of reactants and products change over time. Eventually, when they stop changing, the reaction reached the equilibrium, okay? And we also mentioned that the rate of the forward and reverse reactions, rates of the forward and reverse reactions at the equilibrium point are equal. And this brings us directly to one of my favorite concepts in chemistry, which is a Le Chatelier principle. So effectively, it is an example of negative feedback. Are you familiar with negative feedback? I'm going to explain. Example of a negative feedback in chemical reaction. So negative feedback implies that a change triggers a response that effectively cancels out that change. Okay? So that's negative feedback. So we need to figure out if the equilibrium, if something changes, how do reactions, quote unquote, respond to that? And I have to emphasize, reactions don't have brains or thoughts. They're not living things, so they don't really respond. It's just a chemical principle. So, and the idea is really straightforward. Remember that at equilibrium, concentrations of reactants don't change, and the concentrations of products don't change as well. They're constant. This is the definition of equilibrium. They're not equal, but they are constant. Got it? Now, if you will add or remove reactant to product, in other words, if you will change the concentration, then it automatically means, you see what I'm trying to do here? If this is equilibrium, but then you add a reactant or a product, the concentration changes and it doesn't match the concentration that should exist at equilibrium point. So the rates of forward and reverse reactions will change. And that means that the whole system will be, the equilibrium point will change as well. So this principle, the Le Chatelier principle, is best illustrated by, two vessels that can communicate through that little tube. Okay? At equilibrium, you can see that the volumes, the levels of water in both vessels are the same. If you pour water initially in a tank A, the water will start moving towards tank B until the levels are going to be the same again. Right? Making sense? And the critical thing is that, well, I'm going to highlight something here. You see this statement that the rates aren't going to be the same anymore? For our intents and purposes, I'm going to give you a very brief explanation regarding the reaction rates. Good? So if you have a reaction, let's say A into B, the reaction rate, let's call it V, it is proportional to the concentration of A. Does that make sense? So, the greater the concentration, the greater the rate. Right? So, if you add a little bit more, let's call them reactants, okay? and this is products, right? If you add more reactants, then the reaction from left to right will have greater rate. Okay? But equilibrium will be restored at some point. So here's the idea. In this situation, and I'm going to correct this, this is a reversible reaction which exists in some kind of equilibrium. If you add more hydrofluoric acid, the concentration of hydrofluoric acid will go up, right? And remember what I told you about the reaction rate? So the forward rate is proportional to the concentration of hydrofluoric acid. The more hydrofluoric acid you add, the faster this reaction will go. So if you add hydrofluoric acid, the forward reaction will be faster than the reverse. Okay? So adding more reactant shifts the direction to the products. Okay? Now, what if we remove some hydrofluoric acid? Well, this equilibrium will be disturbed, and since the rate is proportional to the concentration of hydrofluoric acid, it will go down. So we're going to have slower reaction that moves forward, but faster reaction that goes back to the reactants. And if you remove some of the reactant, it shifts the equilibrium towards the reactants back. Okay? Make sense? Cool. And in the same way, if you add more fluoride anion, what's going to happen? The rate of reverse reaction will be greater than the rate of the forward, because the rate of the reverse reaction is proportional to the concentration of the fluoride anion. Right? Make sense? Nice. And what do you think is going to happen if you remove some of the fluoride? Yeah, so let's add lower concentration of fluoride. Okay, makes sense? Reverse is slower, okay? Which means shift to products. So in this reaction, the reverse is going to be slower than the forward one. Sounds good? So this is the summary to where the reaction shifts. You can totally expect these questions to be on the exam next week. But this is an interesting sort of story. You can apply it to a lot of physiological concepts. For example, hypoxia. So you all know probably that oxygen in human blood, it's carried by a protein called hemoglobin. So this is hemoglobin, sometimes called deoxyhemoglobin. And this is oxyhemoglobin, a molecule that already bound oxygen. Okay? Does that make sense? So, when your blood is going through the capillaries in the lungs, through the pulmonary capillaries, there's a lot of oxygen there. Right? Making sense? So, all that oxygen, technically it's not a concentration, it's a partial pressure, but who cares? Okay? Means that the forward rate also increases and becomes greater than the reverse rate. And practically all hemoglobin exists in a form that binds oxygen. Okay? Make sense to you? Now, in tissues, oxygen, I'm going to use a proper term, partial pressure of oxygen is low, which means forward rate is lower than the reverse rate, right? And oxygen is released. Everybody got it? All on the same page? All good? Moving on. So, if I would put you right now at the elevation of 18,000 feet, you would die. Because you would experience hypoxia and there are going to be complications associated mostly with the brain function, stuff like that. Okay? Because the concentration of oxygen is low, making sense? And the rate of the forward reaction is not that much greater than the rate of the reverse. Okay? So, this is indeed one of the most important chemical reactions in the human body. So, if you add some carbonic acid here, in which direction will equilibrium change? Yes, to products. If you remove some bicarbonate, in which direction will equilibrium change? Also to products. Everybody understands why. Go on.
Oh, you're removing. I'm sorry.
No, you're right.
Yeah.
You're right. Everybody understands. Oh, yeah. Do you want me to expound?
Yes.
Of course. Not a problem. So let's consider the first thing, right? A. So H2CO3 H2CO3, carbonic acid, is a reactant. Agreed? Agreed? So rate of the forward reaction is proportional to H2CO3 concentration. Good? If the concentration of H2CO3 increases, therefore, the rate of the forward reaction also increases. Agreed? Which means we can record this as reactants. The rate of forward reaction is more than the rate of the reverse. Clear? Explained? Good? Everyone? Awesome. So this is why there is a shift towards products. Now let's talk about B. Bicarbonate is a product. Agreed? Okay, so when we look at the products, we immediately look at the reverse reaction. Does that make sense or not? Yes? Okay. So the rate of the reverse reaction is proportional to the concentration of bicarbonate, which means that, removing, yes, when the concentration of bicarbonate decreases, the rate of the reverse reaction also decreases. Everybody agrees with that? Good. And it means that if we write this reaction equation, the reverse rate will be smaller than the forward. All good? Now, using the same logic, H3O plus. If we add a little bit more H3O plus, to which direction does the balance shift? So, say again?
Towards the product.
If I ask you, what did you say? It's because I didn't hear it, not because it was wrong. Okay? So, Zach's right. It's going to move towards the reactants. I'll explain in a second. Just check this out. H3O plus is a product. Agreed? So the rate of the reverse reaction will be proportional to H3O plus concentration as well. I just don't include it in our calculations. Did not include this in our consideration yet. Do you agree with that statement? Which means if the concentration of H3O plus increases, the reverse rate increases, absolutely, yes. Which means if we write this equation, the reverse rate is greater than the forward, which means it is shifted towards reactants. All good? Okay. This is the solution. If you don't mind, I'm just going to scroll because this is what we did. Okay, 3 slides. Now you are already prepared to this adult conversation about pH. Okay. So, just to recap of what we were talking about in the lab on Monday. So pH, and I can't emphasize it enough, is an artificial parameter that is used for convenience. Instead of writing some molar concentration, we can use pH. Okay? So it is true that usually pH values are between 0 and 14. Yes, if you will provide someone with 1 molar solution of hydrochloric acid, technically speaking, well, okay, 10 molar will be too much, but if you provide 10 molar solution of hydrochloric acid, technically the pH is -1. But at these concentrations, our assumption that all hydrochloric acid is dissociated will not be entirely correct. This is why we try to keep between 0 and 14. So 7 is neutral, less than 7 is acidic, more than 7 is basic. Okay? And I want to remind you what pH scale is. Remember, right? So pH is a negative logarithm of the concentration of hydrogen ions. pOH is a negative logarithm the concentration of hydroxide anions. And the third equation that you need to remember, pH plus pOH equals 14. You used both of these methods on Monday. You used pH paper and you used pH meter. Which one do you think is more reliable? Of course not. No. Paper depends on your evaluation of a color. If I'm colorblind, and not like completely colorblind, not achromatopsia, like deuteranopia, like I cannot see, I think deuteranopia is like green or something. My interpretation of these results can be totally different from yours.
So like with the meters that we were using, because like everybody was getting like a different pH or like the same amount of like certain things in there.
There was slight variation in pH. And if you use pH meters, those pH meters have a precision level of one decimal point, right? So you can measure 7.4, but not 7.45. pH meters that are usually used in labs, if this is not like some crazy analytical chemistry lab, have a precision of 2 decimal points. There are some that have a precision of 3, but those are very specialized. Okay? So those are the tools that you can use. You can use indicators like this, but you can imagine that it's very cumbersome and inconvenient when you have to prepare a series of dilutions. I'm not going to spend a lot of time on this graph. Nobody's going to ask you what the pH of apple juice is in exam, so don't worry about that. And we're going to jump straight to the calculation. So this is what we did in the beginning of the lab on Monday. Remember when you approached me asking how to do the pH calculations? So just a reminder that if you write this down, logarithm of 10 in a power of x, where x is some kind of a number, the logarithm of this will be x. Not a single sane person. Like if we're talking about 10 in the power of 1, 2, 3, 4, it's easy. If it's like a fraction, 10 in the power of 5.2 negative 4.3, you have a calculator. It'll do it for you. Okay? So, another thing that we discussed on Monday is that the fact that pH scale is a logarithmic scale. Okay. Solution, I'm going to make a statement. With pH 4, okay, has 10 times lower concentration of hydrogen ions than solution with pH 3. Change by 1 unit of pH means tenfold change in terms of the actual molar concentration. Okay? And sort of counterintuitively, the more acidic the solution becomes, the lower the pH is. The greater the concentration of hydrogen ions, the lower the pH. Okay? You can see it in this example. Which of these numbers is larger? 10 in the negative 3 or 10 in the negative 4? 10 in the negative 3. But pH of that solution is 3 versus 4 of this. Questions? Okay. So here, How do you calculate it? You write down that pH equals negative log of 1.7 multiplied by 10 in the power of negative 3. Okay? Making sense? Absolutely. I have no idea. All I can tell you, it's going to be between 2 and 3, but that's about it. So I don't want to move the slide down because, for instance, I'm going to have troubles figuring out how to calculate a logarithm on my phone. So what is the actual pH of that solution? Okay. Okay, perfect. 2.8. That's it. We got our pH calculation. Don't take your calculators away because we need to calculate the pH of the solution with that concentration. So pH will be equivalent negative log of, well, you see 4.0 multiplied by 10 in the power of negative 15. That sounds right. I'm debating myself whether to give you sort of a way to check your calculations, not like the exact way, but do they make sense? So I want to do basically an activity that you probably did in the kindergarten or first grade, but with more complicated numbers. So we have a number, 10 in the negative 15. We have a number, 10 in the negative 14. Does that make sense? And we have a number, 4 multiplied by 10 in the negative 15. I want to put these numbers in order from the smallest to largest. What should be the smallest number? Thank you. Next, larger number. And the largest? Say again? Wait, no. The largest number.
Out of those three?
Yeah.
Oh. 10 to the negative 15. No, 14.
Yes, of course. 10 and negative 14 is more than 10 and negative 15, right? Now, if we would calculate, if we say those are pH, we're going to calculate pH of these concentrations. 15, 14, 14.4. So if your concentration falls in between two adjacent exponents of 10, you're in the right place. Like, if you get like 15.4, something is wrong.
So where did you get the 10 to the negative 14 from?
I just made it up. I just wanted to show you that you can say, oh, okay, my number falls into that category. It's mathematically sensible, right? Now, obviously, you can calculate pH you can calculate the concentration from pH. Does that make sense? If, let's say you have a pH of X, right? So how did you get there? You got there because it is negative logarithm of some concentration in the power of X. Okay? Am I making sense? Yes, of course. Bless you. Let's say we have a solution with a concentration 10 in the power of x mole per liter. Okay, good? So pH will be what? Well, actually, this minus x. pH is going to be x. Okay, pH equals negative log of 10 in the power of minus x, which means it's minus x, which means it is x. Sounds good? Now I ask you how to calculate concentration. You take the value for pH and use it as a negative exponent on top of 10. That's it. Right? Make sense? That's it. So for instance, we have a solution with a pH 3. Does that make sense to you? So the concentration of hydronium cations will be 10 in the power of negative pH. Yes. Mole per liter. Then for that, it's going to be 10 in the power of negative 3.42 mole per liter. Okay? You may be asked on the exam to actually calculate it, to do this calculation of 10 in a certain power. Now, I mentioned that you can use sometimes that equality, that pH plus POH equals 14, right? So you can see that these numbers are negatively, like they related if a pH is 1, POH is 13, if pH is 2, POH is 12, and so on and so forth. Does that make sense? Okay. Now we're going to chat about the reactions between acids, bases, and some other compounds. So acids, of course, react with a lot of different chemicals, but we're going to focus on the reactions with metals, reactions with bases, and reactions with bicarbonate and carbonate. Okay? Does that make sense to you? Now that definition of salt should be placed down on one of the following slides. So we're going to chat first of all about the reactions of acids with metals. I want to correct some of the inaccuracies shown here, like real practical inaccuracies. This reaction is a classic reaction that is done like very early, like in high school chemistry, that shows that interaction between zinc and hydrochloric acid produces hydrogen gas. It will bubble and, evacuate from the tube, leaving behind a salt. Okay, zinc chloride. Am I making sense? So one of the conventions, and you may encounter it later, if we say zinc chloride, we can say that it's a salt of hydrochloric acid. Salt cannot contain hydrogen ions, so HCl is acid, but when H is gone, replaced by zinc, this is salt, okay? And it cannot contain OH minus. So this is a base. See that? But this is a salt. Clear? Say it? Yes. Well, not just hydrogen. The entire OH minus part. OH minus is the base. Go ahead.
What reaction, where are you getting sodium
Oh, this is not a reaction. I'm just writing it. No, I just wrote as an example. No. Just as an example. So what inaccuracies I wanted to highlight? Factual. So if you take a chunk of sodium, which is, by the way, kept under the layer of kerosene, because it gets oxidized by the oxygen in the air almost immediately. If you take a chunk of sodium and throw it in the toilet, the world will have one toilet less, because the reaction between sodium and water releases enormous amount of heat and hydrogen. It literally creates an explosion with fire. Potassium is even worse. If you will try to do this, this is an explosion. They will react. Like, theoretically, not a single person in their right mind will do that. Does that make sense? Because these guys are very, very reactive, especially sodium and potassium. Okay? This will react. So, first reaction, magnesium with hydrochloric acid. Remember, what's going to be produced is salt. I'm not putting any subscripts. And hydrogen. Okay? Let's put subscripts. Go on.
You said for that salt we produce, so in the magnesium
Chloride, this is a salt. It's a salt, yes. So, first of all, hydrogen, did I write it in a proper way? No. What should I put there? Yeah, 2. It's a hydrogen gas, okay? So we have gas, we have aqueous solution, and we have solid. Okay? I'm going to remove that aqueous solution thing. Magnesium chloride. Is it written properly? What should I do? Magnesium, which group is that? 2. So what is the charge on its cation then? 2. Chlorine, which group is that? 17. What is the charge on its anion? Remember, no. Remember, first 2 columns. 1, -1. So 17th group has 7 electrons on the outer shell, and they will accept 1.
So Mg chloride 2?
Correct. Does that make sense?
Is pretty much every ionic compound considered a salt, technically? Or most of them?
Yeah, but the aqueous solution of hydrochloric acid, in solution, hydrochloric acid is ionic compound as well. It dissociates. Kayla, you have a question? Go on.
So, I'm just trying to really understand. So, you have the Mg chloride 2. Is that because it's the second layer?
No. So, okay. So, magnesium, I'm going to put it on the screen. Magnesium has 2 electrons on outer shell. Right? Chlorine has 7 electrons on outer shell. Okay. Remember the formula for groups 13 to 18? You subtract 10. That's it. So you subtract out of 7. So group number, 17 minus 10, 7. Okay. Now, the magic number is 8. For magnesium to reach that magic number, it's easier to give away 2. So magnesium is going to be 2 plus. For chlorine, it's easier to accept 1 to get to 8. So it's going to be chlorine minus. In order to make this compound electrically neutral, the number of positive and negative charges, they should match. So you need 2 chloride to match double charge on magnesium. Good? Now, we can balance it out. Can you tell me just what should I do? So I don't have to write all the things. Like, which number should I put in where?
For A?
I mean, for this entire reaction.
You need a 2 in front of the hydrogen chloride.
That's it. Okay? Does that make sense, Kaylee? So, at this point, you don't need to look at the periodic table. How many magnesiums are on the left? 1. On the right? 1. How many hydrogens right now are on the right? On the left? 2. And chloride checks out as well. Sounds good? Okay, awesome. And then we have aluminum. And I believe that actually, I need to check. I have a gut feeling that aluminum specifically does not react with concentrated nitric acid. I don't remember from top of my head, but nitric acid, although it is a very strong acid, there are some metals that are resistant to it. Some metals that are resistant to it, and they will just not react. Go ahead.
How do you know if it's concentrated or not?
No, I don't. I'm just saying that if they would give us the actual concentration, the reaction would change.
So if anything was concentrated, they would tell you?
Yeah, especially with nitric acid. To correctly predict the products, you have to have a concentration. So the reaction like this, check this out. I'm not going to bug you with that hydrogen thing. We know that it's hydrogen, okay? Good. So we need to balance some stuff here. Correct? First of all, did I write the formula for aluminum nitrate properly? Aluminum, how many charges does it have? +3. Does anyone remember the charge on the nitrate? -1. How many nitrate anions? This is from the table. It's not from periodic table. Remember? Okay. Remember we're talking like HNO3. So this polyatomic anion has a charge of NO3 minus. We're trying to figure it out, like the charges. You pretty much memorized it. So NO3 has a charge of -1. How many nitrate anions do I need then to balance 3 positive charges on aluminum? 2 more? Sure. Which makes the total number 3. Does that make sense? Okay. What I need to do next about coefficients? What coefficients now? Everything is written properly. Now I need to balance this reaction. Tell me. Go on. Far away. I'm going to do whatever you tell me.
3 in front of the
This? Okay.
So like 1 in front of the and then
Well, you don't need to put 1. It's already 1. Go ahead, Alicia. What else do I need to do? Can I put 1.5? Oh, come on. Look. Watch me. I just did. Is it correct? What do I need to do to make coefficients the integers? By what? Say again? Like multiple. It's going to be 4.5 on the left. You mean here? 3 on the right?
Or 6, and then you can put a 2.
Where? Here? Just tell me in front of what? Let me go back to your previous stuff. Look, if you have hypothetically a fractional coefficient, what do you need to multiply the entire equation by? Which number? Number 2. Look, I'm going to multiply each and every component by 2. 2, right? If I multiply 3 by 2, what do I get? 2. 1.5 by 2. Check the balancing. Checks out. Aluminum's on the left. On the right. Hydrogen's on the left. On the right. NO3's on the left. The entire thing. 6. And on the right, 6, because 3 by 2 equals 6. Unless I get the confirmation that it makes sense from all of you, I'm not moving on. Okay? So if you mix acid, more or less strong acid, with carbonates or bicarbonates, that will produce carbon dioxide in water and a salt. Sounds good? You observed those reactions this last Monday, I think. Okay, this is like that volcano experiment that everybody does in like 3rd grade or something. That's exactly it. So, magnesium carbonate plus hydrobromic acid. Tell me the products. If it's carbonate, what's going to happen? They're going to form salt. Yes. Look. Salt, carbon dioxide, water, right? What salt are you going to form? And what's going to be the anion? Bromide, yes. And then you're going to have water and carbon dioxide. Right? So far, so good? Okay, cool. Did I write the formula for magnesium bromide properly? It needs some modifications. If in doubt, look at the periodic table. Magnesium, which group? How many charges? Plus. Bromide, which group? 17. So how many? 7 electrons. 1 minus, because it will accept 1 electron. How many bromide anions total do I have to have? Yes. So again? So this salt must be electrically neutral, right? The positive charge is 2 plus. You have to balance it with negative charges, but each bromide gives you only 1 negative charge. So you need 2 bromides. Making sense? Okay. What do I need to do to balance this reaction? Remember, you're focusing on hydrogens, and like it's a very last thing to focus on hydrogens. Does magnesium check out?
Yes.
What about bromide?
Yeah, 2 to the 8, the hydrogen.
Anything else? Don't try to read my voice. I'm asking you anything else. Nope. All good. All balanced.
What about like for like the CO3? Would you have to like change?
How many? Say again?
Would you have to change the CO2 on the other side to balance the
No. How many carbons are on the left? Clear. How many carbons are on the left?
3.
No. 1. How many carbons are on the right? 1.
Okay.
How many oxygens are on the left?
2. Oh, 3. Sorry.
3. On the right?
2.
Nope. 2 and 3.
Okay.
Does that make sense?
Yes.
Okay. Hydrochloric acid plus sodium bicarbonate produces obviously water, carbon dioxide, and which salt? Na. Yes, sodium chloride. Anything to do anything with this? How many sodiums are on the left? On the right? Chlorides on the left? On the right? Hydrogens on the left? 2. On the right? Oxygens on the left? On the right? You good? Does that make sense? And finally, neutralization. This. So acid reacts with base, always forming a salt and water. By the way, quick thing about this reaction. You're familiar with TUMS? TUMS, T-U-M-S, the tablets. This is exactly what they're doing. When you have like acidity and, acid reflux, well, you're young, you don't know what it is. But TUMS is, and you're going to feel a little bloated because you're going to have carbon dioxide produced in your stomach. Okay. So now we're going to talk about neutralization reactions, and we're going to learn about net ionic equation. Okay? So look at this reaction here. Hydrochloric acid, HCl, is a strong acid, which means in the aqueous solution, it exists as individual ions. Make sense, right? Same is true for sodium hydroxide, which in aqueous solution exists in a form of individual ions. So those ions are kind of floating around. Does that make sense to you? When hydrogen ion hooks up with hydroxide anion, they form water. Does that make sense? Now, chemical reactions to a large extent work pretty much just like arithmetic equations. So if you have sodium on the left and sodium on the right, you can cancel them out. Chloride on the left and chloride on the right, you can cancel them out. And this produces what's called net ionic equations. Ions that are present both on the left and on the right are cancelled out. Okay? So, neutralization reactions. Let's take a look. How should we balance this? So, what would be the most obvious thing to do? So again, you can't. Well, actually, we're not going to cancel aluminum. Well, we will eventually, but we need to write a complete reaction. So how many hydrogens are on the left? Oh, sorry, how many hydrogen ions produced by HCl? One. Now, aluminum will give you this. Does that make sense to you? Because each formal unit of aluminum hydroxide will give you this. Okay? So 3 chloride anions from aluminum chloride and water. Now, we can cancel aluminum. That doesn't bring us closer to balancing that reaction. Okay? So what should we do to get to 3 chloride anions on the right? Yes. 3 what? Where should I add 3? On the other side. In front of which product? I'm not going anywhere. Okay. Hear me out. Chloride. All good? Okay. Aluminum all good? How many hydrogens currently is on the left? Dude. Nope. How many hydrogens? 3, 6. Yes. It's okay. How many hydrogens? So on the left, we have 6 hydrogens. Everybody agrees with that? How many oxygens on the left? 3. How many hydrogens do we have on the right? Oxygens. There's obviously a number 3 here. Go ahead.
Canceling out was it chloride?
We will eventually cancel it out, but we need to balance the reaction first.
So when you cancel out, it doesn't matter that one has a 3 and this one doesn't only has 1.
No. I can't cancel them until they are balanced. When they are balanced, I can do it easily. If I put 3 here, and 3 here, and 3 here, please be my guest. Okay? What about this? This is lovely. So let's write the entire ionic equation, shall we? So barium plus 2OH minus plus 3 hydrogens plus PO4, 3 minus, 3 barium ions, right? Plus 2 PO4, 3 minus, plus water. Remember, this is unbalanced reaction. Okay, makes sense? Now, you see this little remark here? Solid. It is. This salt precipitates. The reason why I split it in ions is just to balance the reaction. Okay? So if we have 2 PO4s, right? How many PO4s do we have on the left? Just 1. So we're going to put 2 in front of it. Right? Makes sense? So 2, and now it's going to be 6 hydrogens. Okay? How many barium do we have on the left? No, on the left 1, on the right 3. So we're going to put 3 in front of barium. Correct? Making sense? And I need to change this to 6. Right? Barium, does it check out? Yes. Phosphate, PO4. Yes. What we need to, last modification that we need to provide is what? We need to adjust which? Yes. We have 6 OH minus, 6 H plus. How many molecules of water it's going to generate? 6. Make sense? So the answer is this. Sounds good, folks? Okay. You already worked with buffers. Buffers maintain the pH of a solution. Okay? Now, the pH does not change when acid or base is added. It's not going to change in a certain range. If you will, pump the solution with concentrated hydrochloric acid, it's going to overcome the capacity of a buffer to neutralize the changes. Okay? So, the buffers, as we discussed in a class briefly, they absorb acid or base. Okay? And in humans, they maintain pH of the blood and intracellular fluid at about 7.4. Okay? And the buffer usually contains a weak acid, okay, and its conjugate base, okay? Acetate is the name of that anion, okay? And this is really important. Equal concentrations of a weak acid and the salt. So, for instance, you have this, go ahead.
One thing that's confusing me is, I thought sodiums, or salts couldn't have hydrogen. You know what I mean?
Okay, so I see where confusion is coming from. They can. Well, first of all, this bicarbonate. But strictly speaking, acetate, this, is an organic compound that looks like that. Does that make sense? So this entire thing is acetate. This is how it structurally looks like. So
because it's like a polyatomic.
it's polyatomic anion, the entire thing, yes. Okay?
It wouldn't have any just separate hydrogen.
No. These hydrogens are not participating in these ionic processes. Okay? So, what do you essentially make? You make a solution which contains a certain amount of acetic acid and a certain same amount of acetate, the conjugate base. Okay? Sounds good? Now, I have a question for you about equilibrium. When the reaction is in equilibrium, the concentrations of products, acetate, and the concentrations of acetic acid, do they change at equilibrium? They do not. So by providing equal amounts, we select the best equilibrium point for a buffer. Okay? Now look what happens when we add some base to the buffer. Remember in the neutralization, right? The base can be neutralized by the acid. Okay? So you reduce a little bit the amount of acetate and increase a little bit the amount of conjugate acid. Okay? That provides you with the capacity to effectively cancel the effects of an added base on the pH of the solution. So despite the fact that concentrations are slightly different, pH remains the same. Am I making sense? Now, the function of the acetate ion is opposite to neutralize acid. You add acid, acid is absorbed by the acetate, ion forming acetic acid and water. Does that make sense to you? I don't remember if they... So this is the way the buffer works. If this buffered solution receives a dose of acid, it a little bit depletes the conjugate base and increases the weak acid concentration. If it receives the dose of a base, it depletes weak acid and increases the amount of conjugate base. Before we move on, does that make sense? Okay, so let me ask you this. I make a buffer. And this is the pH of the buffer. Sounds good? This is the pH of the buffer. I start adding more and more acid. When I start dropping like 1 drop of acid in the buffer, since it's a buffer, will pH change? But as I add more and more and more acid, will it eventually overcome the buffer capacity? Does that make sense to you? So if I start adding, each buffer, depending on its concentration, has a certain capacity to absorb certain amount of acid or certain amount of base. It's not infinite. Make sense? Now let's address this question. So which of these 2 pairs, well, 4 pairs, I'm sorry, can serve as a buffer? Hit me. Okay. You think so?
Because...
Same anion, you're right, but...
Or no.
No, why? HCl is an acid, but what acid is that?
It's a strong acid.
Not a buffer. Carbonic acid and bicarbonate. Yes. That's a weak acid, and that's, so we can say that carbonic acid, H2CO, yes, H2CO3 dissociates into H plus and HCO3 minus. Does that make sense? So that's your conjugate base, that's your acid. What about answer C? No, it's not going to work because ions and ions are different. What about answer D? Huh? Because phosphate and chloride are 2 different anions. It should be an acid. So this is acid, right? If instead of sodium chloride, bless you, I would write down sodium dihydrophosphate, that would work.
So the anions have to be the same in order for it to...
Because it's the salt of the weak acid. Okay? Serves as a conjugate base. What about D? Will it work? Yep.
That's a weak acid.
Oh, it is. It's acetic acid. It is acetic acid. Okay. Questions? All right, folks. We're going to take a break and come back and talk about some exciting stuff.